Okay, good. Yeah, I'm going to be talking about a multispectral camera that we're developing with Dolly funding from NASA. So next slide. And talking about imaging observations from the surface, conventional RGB, red, green, blue color is of pretty limited scientific use. Of course, we get morphology images, which are quite useful. But as far as the color data, the typical filters in such a camera are very broad, they're closely spaced, and they overlap quite a bit, as you can see in the plot on the left. And therefore, they don't capture key lunar spectral variations, things like band depths and slopes. This is illustrated in the spectral plot on the right that shows the major silicate lunar minerals. And of particular importance is the ferrous iron absorption band that's located at wavelengths between about 900 and 1,000 nanometers. So to overcome that, next slide. What we're working on is this Mahina multispectral imager. Mahina is the Hawaiian word for moon. So this is a COTS-based CMOS imager, which is sensitive from the visible to the near infrared. And what we will do is to install custom lunar-specific filters in a Bayer-like pattern that allow us to do snapshot imaging. So our baseline filter set is 430, 750, 940 nanometers. And these are similar to filters that have been used on missions like Clementine and a number of others for quite a long time to extract the composition of the surface, in particular the iron and titanium content, and also the optical maturity parameter. And furthermore, in 2023, there was a paper that defined a set of soil classes for resource utilization. They're defined based on composition and particle size. And the author of that paper, Kevin Cannon, demonstrated that these resource soil classes can be mapped with this kind of filter set. So the figures in the center and on the right just illustrate the nature of this Bayer-like pattern that will be affixed directly onto the focal plane array. Next slide, please. So as for the science that can be done with a camera like this, of course, composition and maturity mapping, right? The iron, titanium, OMAT maps, which can be used to study the, site geology, the processes that have taken place, including, impact cratering, volcanism, space weathering, dust, modifications to the surface by landing rocket exhaust. And as the rover, moves from place to place, we can really just chart the evolution of regolith from fresh rock to mature soil. Now, the image on the lower left illustrates just the tremendous spectral richness that is revealed when you have 3 filters at well-chosen wavelengths. So that's the near side of the moon there, and you can see there's quite a bit of spectral diversity that comes out of just 3 filters. And what we want to do is to bring that type of well-proven orbital mapping capability to surface scenes like the one that you see there on the right, with the boulders and regolith and the impact crater in the background. Next slide. So some additional science. So specifically in the South Polar region where the pressurized rover will be operating, we could adjust the filters somewhat to specifically focus on highland mineralogy. And something else that's of extreme interest is hematite detection. So this was reported in a paper about 5 years ago, but hematite is an alteration mineral that contains ferric iron. And, surprisingly, this could involve interactions with oxygen that's been swept down the magnetotail to the moon from Earth's upper atmosphere. So it's really important to investigate the geologic and topographic setting of hematite. And again, this could be a useful resource for iron. The plot on the right is just a simple pair of spectral ratios that illustrate that it should be fairly straightforward to detect hematite apart from the more common lunar minerals, just using these spectral ratios. Next slide. Next slide, please. Okay, then something else that's of great interest is horizon glow. Now, this was observed shortly after sunset by the Surveyor 5, 6, and 7 landers back in the 1960s. What it's thought to represent is light being scattered from electrostatically levitated dust that's on the horizon after the sun has gone down. And we clearly need new observations. An instrument like Mahinacam, is going to be radiometrically calibrated, which is essential for modeling the dust abundance. And our multi-wavelength images will further constrain the size of the dust particles. On the right, you see this lovely image just recently returned by the Firefly lander. It may be possible to extract some science from that, but essentially cameras like this are just touristy vacation snaps, and you really need a real radiometrically calibrated science instrument to do the quantitative analysis. Now, the poles are particularly interesting for this because, first, given the long duration of the pressurized rover's lifetime, and then polar lighting conditions, there are going to be many opportunities for observing, terminator passage, the sun temporarily moving behind local topography, and sunrise, sunsets, and so forth. Okay, next slide. The placement. As we saw, there's going to be these external mounting positions. I think the one shown there in the diagram would be good. For the PR opportunity, we would probably propose a stereo version because stereo is important because it can provide these co-registered digital terrain models, which is good for the geology, but also for photometrically normalizing the image reflectance values, because you'll have the solar incidence and the emergence and phase angles for every pixel. We could include different filters in the left and right eyes to expand the number of spectral bands, and probably a 1 degree of freedom pivot to increase the field of regard. The instrument's pretty low mass, low power. The numbers that you see there. Okay, on to one more slide, I think, at least one more. This is a instrument development campaign that's ongoing right now. We have a few hardware pictures there. We recently conducted single event proton radiation testing. We have our 4 optics designed, and we'll be sending those out for manufacture soon. There's a drawing of the camera housing there. You can see how small it is. That would just fit in the palm of your hand. So the Mahina multispectral camera is going to be ready to conduct wide-ranging science on the pressurized rover. Is that the last slide? Might be.
Yes,
is that the last?
It's the last slide.
Okay. All right, then I'm done. Thank you for your attention.